Today on the Serial Port, we're taking a look at a little-known company that defied the odds. A company that took a gamble with an ace up their sleeve. A gamble that paid off big. This is the story of ALTEON. $1995 was a big year.
I just want to give it a whack, see what it's all about.
The Sony PlayStation arrived in the US, Amazon sold their first book, and Ethernet got fast. Almost as soon as it arrived, though, there was already a race to develop an even faster Ethernet, and breaking the 1 gigabit barrier was the next target. The need for faster speeds arose from bandwidth limitations for growing networks in ISPs, enterprises, and campus environments. For many backbone needs, ATM or asynchronous transfer mode was seen as the future because of its rich features designed to support voice, video, and data over a unified network. But Ethernet proved resilient. Its vast installed base, simplicity, and ubiquitous nature meant that furthering its development was inevitable. That's why in 1995, the IEEE Standards Organization started work on a new standard for this higher speed, but it was still years away from being completed. But despite this, a slew of companies were already looking ahead.
So there was just this huge explosion of companies. Most of them were doing switches. There was a few that were also doing NICs. The race you see today of everybody jumping to the AI space, the race in the mid-90s was all about networking.
And that's where we meet John Hayes. In the early 90s, his work was on the bleeding edge of networking technology at the time, and he would later go on to co-found a company called ALTEON Networks. But his start with computers had a more meager beginning.
I was in high school. I had a 300 baud modem connected to a VIC-20. This is like early 80s, and I think I was dialing up CompuServe. And that wasn't even really the internet then. That was like the pre-internet. The first company I worked for was a company called Ultra Network Technologies, which is sort of the beginning of the whole ALTEON thing as well. And Ultranet was started in the 80s, and Ultranet provided the first 1 gigabit network. So think about that in the context of, late 80s and early 90s. So we basically connected Crays, IBM mainframes. Those were in the various supercomputer sites and any places that somebody needed bandwidth, network bandwidth. Those were the days of 10 megabit Ethernet. So a gigabit was, 2 orders of magnitude above that.
These cutting-edge applications needed lots of bandwidth, far more than what Ethernet could provide. And that's what Ultra Network Technologies specialized in.
And that's sort of where we got started, and that's where I met the other founders of what became ALTEON. Mark Briers, Ted Schroeder, and Wayne Hathaway.
Hayes and his future co-founders left Ultra Network Technologies in 1993 and started working as consultants for a company called Essential Communications. Essential was founded by Michael McGowan, who previously had helped create the HIPPY protocol at Los Alamos National Laboratory. Developed in the late 80s, HIPPY stands for High Performance Parallel Interface, and it used either copper or fiber optic point-to-point links that achieved an incredible 800 megabits per second transfer rate. Hayes was working on firmware for HIPPY interface cards, with Mark Briers working on the chip design and Ted Schroeder on software. But in 1995, Hayes and the other consultants began to see gigabit Ethernet as their future, and decided to focus on it for a new venture.
So Essential is not a big company. It's another startup. Mark convinced them that, listen, we're not going to build your next generation, so the best thing you can do is license it to us.
And in March of 1996, ALTEON Networks was born.
So we actually licensed all the technology we built, went out and made the VC rounds in Silicon Valley, and that was the beginning of ALTEON. At the time, it was called ALTEON Networks, and we were building NICs and switches. We really knew the NIC side of the business, the host interface side, but we thought we could never get a NIC company financed. So we had to present it as we can do NICs and switches. What was funny is while we were making the VC rounds, they, the VCs would say, well, how do we know you guys can do this? So we'd pull out the hippie card from Essential and say, well, this is working and it's pre-standard Ethernet. I mean, because we'd already demonstrated it's running 800 megabits. The biggest thing that needed to be done was changing the Mac from a hippie Mac to an Ethernet Mac, and one that was compliant and all that with the upcoming, the expected, I should say, IEEE standard for gigabit Ethernet. Our initial two backers were Sutter Hill and Matrix Partners, both in Silicon Valley. I think it was about $4 million. So that seemed like a lot in the, in 1996. So yeah, those guys got us off the ground.
Based out of an office in San Jose and armed with $4 million of funding, they set off on their mission to develop gigabit Ethernet products. But they weren't the only ones. As members of the Gigabit Ethernet Alliance, there were now dozens of companies looking to develop gigabit. Leveraging their previous experience with Hippie, they were able to quickly build a NIC. But being in uncharted pre-IEEE standard territory, everything was custom.
About a year into it, we actually had NIC hardware, meaning, and by the way, at this time, there were no off-the-shelf ASICs for everything. We had to build full custom ASICs. FPGAs weren't nearly fast enough.
And they were about to make a decision that would change the course of their company.
When you're young and stupid, you don't realize how hard things are.
The custom ASIC they developed was based on the MIPS R4000, but with different opcodes or operation codes to avoid copyright issues.
There was a bunch of other hardware in there. It was basically your DMA engines and your Mac engine. So you queue things up for them to do, and then they'll signal you back when you're done. And all of that was managed in a bunch of registers, some of which could be controlled by software. The rest of them would basically tell you completion status. So at the very bottom of this thing was a roughly 9 instruction loop that was a priority encoder of the status bits and then jumped to the various handler.
Even though there was a lot of hardware supporting it, the NIC still heavily depended on software in order to function, and wouldn't work at all if the processor was turned off.
So it was essentially a software NIC with lots of hardware assist.
This newly developed chip was dubbed Tygon, and found its first home in ALTEON's ACE-NIC, one of the first gigabit Ethernet adapters available. Gigabit Ethernet at this time used a fiber optic interface, as the signaling for twisted pair had not yet been able to reach these speeds. Not intended for desktop applications, there were only specific use cases where gigabit speeds were even needed, typically on high-end servers when running bandwidth-intensive tasks.
We were also doing very well on the NIC side of the business, but nobody heard of us as a NIC company because it was all white label. So we had OEM deals with IBM, HP, 3Com, SGI, eventually Dell. There was a period of time during the Tygon 1 where we had something like 85% of the market.
ALTEON's new chip and later versions found their home on many of the gigabit NICs of the time, such as Sun's Gigabit Ethernet adapter and the 3Com Gigabit Etherlink 3C985. And while they had a NIC, there was still a gaping hole in their product roadmap, a switch.
The switch side of the business was not making enough engineering progress. So it's like, we need to get a switch out. We started off by mocking up a switch using a bunch of NICs, just breadboarding it out, got it running, and said, we need to demonstrate a switch prompt. So the first switch was a switch built out of NICs. So it was an 8-port device. It had 9 of our parts on it. So one for each port, and then a separate one for management. It was actually internally connected via PCI bus, but to limit bus contention, we also put a bridge in the middle so you could have 2 halves operating independently that didn't contend with each other.
Dubbed the Ace Switch 110, it was a $9,000 Layer 2 switch with 8 10100 ports and 2 gigabit fiber optic ports. It also introduced support for jumbo frames. An ALTEON developed a method of sending Ethernet frames with a 9 kilobyte payload, nearly 6 times larger than the official 1,518 byte maximum size, reducing packet processing overhead. Since Gigabit Ethernet was still in its pre-standard phase, ALTEON needed to show the NIC and switch working in conjunction. They debuted their new solutions at the 1996 NetWorld Interop show in Atlanta, Georgia. The demonstration would include a NetApp F540 filer outfitted with their ACE NIC, connected to the new switch with several client workstations on 100 megabit connections. This was the world's first public demonstration of Gigabit Ethernet technology. But for the following year's show in Las Vegas, they had to up the ante. Instead of just a demo, they would employ both the ACE switch and ACE NIC to provide key services to the vendor booths for the entire show, including streaming video and DNS. This was supposed to be Gigabit Ethernet's big moment, a key test that would show the world that Gigabit Ethernet was ready. But it quickly turned into a fiasco.
Suddenly, these switches started failing. So we go around and realize that the new switches came in, whoever built the case neglected to put the air holes in. So the switches were cooking themselves. So I go out and I get a drill, and I'm afraid these things are already cooked. So I'm pulling the switches out of the rack. I am literally just ramming the drill in the side, drilling holes. There's bits of metal. Luckily, the PCB boards had been sealed, so I'm not causing a short. But I ran around and I created metal shards from every single one of these switches. We put them back in, and they ran for the rest of the show.
Having survived the harrowing experience of interop, ALTEON's next step was to actually get a switch out into the wild to see if Gigabit worked in the real world.
And a friend of mine, George Hall, had an ISP in Sacramento. We hadn't even released the switch yet. We needed to show a sale of a switch. So we drive up there, deliver a switch, thinking George is going to go put it on a test network. George pays us a nominal amount for the switch. So now we've recorded a sale for a switch. This is the first switch sale ever. And George plugs this thing right into the internet and just goes live, which was quite funny. So that made George and SNA to be the first ISP to have a gigabit network plugged into the internet.
The ACE Switch 110 picked up attention from the industry, with Sun using ALTEON as the OEM for its own Sun Switch product. However, even with these successes, the switch didn't compare all that favorably to others.
So we had this layer 2 switch that worked, gigabit Ethernet, and because of the architecture on a per port basis, you had local memory and processing, but it made a lousy layer 2 switch. I mean, layer 2 switches are basically dumb. I mean, they just do forwarding, they've got your forwarding database, all that stuff, but they're pretty stupid. We were having difficulty of competing with other people that were coming out with just pure hardware layer 2 switches that didn't have any flexibility and functionality.
Because of its software-reliant architecture, the switch performed poorly with minimum packet sizes at maximum rates, exactly the types of tests that would be used to stress test a layer 2 switch. And with products from competitors stealing the spotlight, ALTEON's bright gigabit future suddenly looked bleak. But sometimes with disaster comes opportunity. By the late 90s, the explosive growth of the World Wide Web was bringing millions of new users online, putting immense pressure on the internet's still developing infrastructure. Popular websites struggled to handle the ever-increasing traffic. This quickly led to the World Wide Web being rebranded as the World Wide Wait. In order to cope with the onslaught of new users, ISPs were desperate for new strategies.
Some folks from ALTEON were visiting an ISP, and the ISP was saying, I've really got a problem with web cache redirection, meaning I need some stuff to be steered around, and there's no parts that can do this.
Web cache redirection is a technique that stores frequently accessed content, like a news website, for instance, on an ISP's local server. When a user's browser requests that website, a caching server would intervene and serve the already cached content in response, eliminating the need to contact the remote server and saving valuable bandwidth. And the need for an ISP to leverage content caching created a new challenge: how to efficiently redirect traffic to those cached servers. But in the midst of their meeting, ALTEON had an idea. The Tygon chips, with their heavy reliance on software, meant they were very flexible, if nothing else. They could easily be reprogrammed to perform different tasks, something that wouldn't be possible with the fixed function hardware pipeline of a traditional switch. So why couldn't they adapt their switch to also handle web cache redirection? Suddenly, their Achilles heel started to look like their way forward.
So I think that meeting would have been on a Thursday or a Friday. By Monday, they prototyped it because this is all software, and we were able to demonstrate flexibility and started steering the traffic.
Popular websites faced another challenge: how to distribute incoming requests across multiple web servers. Scaling up had given way to scaling out. That is, adding more servers to handle load rather than simply upgrading an existing one, especially with the advent of lower-cost x86 servers running Linux. Adding more servers was all well and good, but the challenge came in how to distribute users across those servers. At this time, load balancing was a relatively new concept, and there weren't refined solutions like we have today. And while Cisco may have developed the first load balancer product with the local director released in 1996, the demand for load balancing couldn't be overstated. ALTEON's combined hardware and software stack quickly evolved into a new offering.
The thing that made the ALTEON switch unique, what enabled us to do this and to do it at speed, was it was software, and not only was it software, but as you added ports, you added CPU power and local memory. And then the challenges end up being, how do you do health check in a meaningful way? And also, when you have affinity, how do you make sure you steer the traffic to the right server so that if I have a shopping cart on one machine and I come back later, how do I go to the same machine? The back-end architectures in the late 90s and early 2000s, it was much easier for a performance perspective if you could provide some continuity because the back-ends weren't nearly as fast.
The ACE switch could now operate at layer 4, allowing the switch to examine the IP address and port to determine how to route the packet, meaning requests on port 80, for example, could be distributed between different servers automatically, utilizing health checks to the backend servers to balance the load.
In the load balancing, you don't take a load balancer and spray it with maximum bandwidth, minimum packet size things. That's not the sort of thing you do to a load balancer. So nobody cared about that anymore. And we had the flexibility to do this faster than anybody else. I mean, the thing that allowed us to succeed was a combination of features and performance together.
With the advantages of load balancing now being realized, the industry quickly grew, with entries from companies like F5 and Radware. And with ALTEON's new load balancing capabilities, the Switch product pivoted to become the ACE Director. ALTEON introduced the ACE Director 1 in January of 1998, which used the same hardware as the original ACE switch. No longer focused on just gigabit, the new load balancer provided 8 switched 10100 ports, along with web cache redirection capabilities, drastically simplifying a provider's infrastructure by combining all of this functionality in a single device. This was followed up by the $15,000 ACE Switch 180, presented as a server switch for Layer 4 load balancing. Each port on the switch used their new Tygon 2 ASIC, which now featured 2 RISC cores, enabling the switch to process more than 400,000 TCP connections per second at full line rates.
Is it fair to say that load balancing wasn't part of the roadmap, like when the company was first funded and the company pivoted?
Oh, absolutely not. I don't know that load balancing really existed then. I mean, I wasn't aware of it. This was not planned, but we were able to take advantage of it and then go do good things with it.
Their new focus came with a name change as well, as they transitioned from ALTEON Networks to ALTEON Web Systems. No longer just a networking company, they started using the term web working and marketing and also developed a global load balancing solution. The GLB was taking load balancing a step further and steering traffic at the DNS level from end users to data centers. Around this same time, a new startup called Equinix was establishing its Internet Business Exchanges, backed by industry giants Cisco and Microsoft. Equinix's first Silicon Valley data center, SV1, stood at 11 Great Oaks Boulevard, practically neighbors with ALTEON's own headquarters. Given ALTEON's role in the emerging load balancing market, it's likely their devices would have been found here to help manage the surging volumes of internet traffic. This wave of success culminated on September 24th of 1999 when ALTEON went public and raised $76 million.
I say we got very lucky, meaning that was near the peak. So it was end of 99 and things started falling apart 3 or 6 months later. When I say falling apart, the internet bubble was bursting. But no, we got lucky. I mean, yes, you have to execute, but then all the other conditions have to be right as well. The IPO was, that's every startup's dream, is to have a successful IPO.
And on July 28th of 2000, Nortel announced an agreement to purchase ALTEON Web Systems for $7.8 billion, capping off a 5-year whirlwind. But even this incredible success story wasn't immune to the effects of the dot-com crash, as the initial $7.8 billion dropped to $6 billion when the deal with Nortel was finally closed in October of that year. But that wasn't the end of the story for ALTEON. The last generation of their Tigon architecture, Tigon 3, ended up becoming part of Broadcom's BCM 5700 series, one of the most prolific gigabit Ethernet controllers of the time. And in 2009, Nortel ended up selling the ALTEON line to Radware, where it continues to this day.
The whole thing was absolutely like a rocket ship ride. I mean, for the first 2 years, inclusive of weekends and holidays, there was something like 10 days that I wasn't in the office working on stuff. I mean, this was a all-consuming thing. And we had fun. I mean, we had to me, this whole thing was a lot of fun. I mean, we learned a lot. I had a great team of people and had fun doing it. And yeah.
To celebrate their achievements, we've acquired an Ace Director 2, an $11,000 load balancer released in July of 1998, at arguably the peak of their tenure. And it's branded ALTEON Networks, so this is before the name change to ALTEON Web Systems. Taking the lid off, we can see an architecture exactly how Hayes described. There is a Tigon 2 processor and memory array for each of the 8 10100 ports, along with a 9th processor for management. There is a footprint for a card slot on the PCB and a cutout in the chassis, presumably for adding gigabit capability. Because of its inherent flexibility, ALTEON most likely used this board for several different models and installed gigabit ports as needed. But let's power it on and see if we can get started with load balancing. connecting to the DB9 console port on the front with a null modem cable, we're greeted by the unit's firmware and quickly arrive at a password prompt. Fortunately, the default password of admin works. From the main menu, we can see that this is a unique command line interface, and on the face of it seems easy to navigate and understand with a short explanation of the commands. However, once we got started going through the network configuration, it's a little bit puzzling due to a somewhat murky relationship between physical ports, VLANs, and IPs. The diff command shows changes that have been configured, and then the apply command will apply them. Save will save the configuration, and it seems that some changes only go into effect with a reset of the unit. And thankfully, the unit reboots extremely quickly, literally just a few seconds. After fumbling through a few false starts to get a load balancing environment working in the CLI, we were also able to check out the web UI or browser-based interface, which wasn't particularly helpful at this point. We couldn't find documentation for this software version, which is version 5, but we did find a command reference guide from 2001 for version 9. One important aspect is that whatever physical ports you are using have to be explicitly set up to handle either client or server traffic. We're going to use our compact ProLiant 6500 as the single server to start with, and we'll have a front-end and back-end network. The ALTEON has its IP address on the front-end network, which will just be used for management. A virtual IP or VIP will also be added to the front-end network, and this is the IP that will be load balanced. It is mapped to a virtual server. And finally, one or more real servers are on the back-end network, which in this case is the ProLiant and is grouped into a real server group. The ProLiant, which is our first real server, can successfully ping the ALTEON. It's set to use the ALTEON as its gateway, since all return traffic to clients will need to go through the ALTEON since we're using a NAT-based approach. And a key last step is to configure the ports in the SLB or server load balancing menu. Port 1 connected to our front-end network is set to client mode, and port 8 for our back-end network is set to server mode. These settings are necessary to make the NICs play the correct role in the overall layer 4 header rewriting work. We enabled health checks on the real server so the ALTEON will only start to forward traffic to it once the health checks are successful. The health check is done at layer 4, so we won't see an HTTP request logged, but using TCP dump, we can see the TCP connection indicating that the health check is working. And now, sending requests to the virtual IP, we can see them processed on the compact. It's working. But of course, it wouldn't make sense to have only a single real server, so we're adding in our Ubuntu lab machine to complete the demo. This machine has a relatively recent Core i5 processor with 4 cores, so it will be interesting to see how it compares to the much older 4-way P3 Xeon. And with traffic being distributed to both real servers, we can see that the load balancing is working. And the stats seem to show that the newer lab machine is handling an order of magnitude more requests than the compact. But with that, the first serial port load balancer is online and working. When we first got the ACE Director 2, we initially just wanted to see if we could get it working. But that was before we learned about the unbelievable story of ALTEON. For a company with so many firsts, they are undoubtedly one of the many unsung heroes of the .com era. And it was all due to that original team that worked tirelessly to turn what was just another gigabit company into an ace. That about does it for the ALTEON.
For now, yeah. It's a fun project.
Yeah, it was a lot of fun. Anyway, I think that about does it for the ALTEON ACE Director. We'd like to give a special thanks to John Hayes for telling us all the stories from ALTEON. And anyway, thanks for watching, and we'll see you next time.